All right, let's get started with what we have to cover today. So I know many of you have more pressing concerns in this course, but we have some new stuff to get through, which we'll start with now. So the exam is going on right now, as you guys know. If you have any last minute questions, I'll be around most of the day, rest of today. Tomorrow I should be around most of the day. So feel free to stop by even if it's not during regular office hours. But today, if you could do me a favor and wait till like 1:30 or so after class, that'll give me time to record the homework review, which I haven't had a chance to do yet. So I'll knock that out, and that'll help some of you as well. And then I'll be available for questions and stuff the rest of the day if you need to come by. So what we're going to talk about today is what's called Hess's law and enthalpy of formation. So we closed last time with learning how to add chemical reactions together, where if we have two different chemical equations, we can combine them into one by adding the reactants and the products and canceling out anything that's an intermediate. And it may have been unclear why we're doing this or what's really the point of that. But what it allows us to do that we're going to see today is if we have some unknown enthalpy, so if we know the enthalpy change for two chemical reactions and we want to find the enthalpy change for another reaction, we can add the two reactions together and then use the properties of the change in enthalpy to allow us to calculate the enthalpy change for the reaction where we don't know it. And this way we don't have to necessarily then go into the lab and measure every single enthalpy change that we're interested in. We can just measure certain types of reactions and then combine them with each other to calculate an enthalpy change for anything else we're interested in. So let's first review some of the properties of delta H, which we're going to need to consider when we're doing this. So we talked about the sign of delta H, and that's determined by whether the reaction is exothermic or endothermic. All right, and we saw that both are possible. You can have either positive or negative values for change in enthalpy. So exothermic reactions have a negative delta H, endothermic reactions are positive. So that's the sign of delta H, and then the magnitude of delta H, and we kind of talked about this in the context of calorimetry. This is proportional to the amount of substance that's involved in the reaction. And so, when we're talking about running calorimetry experiments, if you burn 1 drop of gasoline, you're going to get a small amount of heat. If you burn a gallon of gasoline, you're going to get a lot more heat, a lot more enthalpy change. So let's say, for example, we're burning water, let's say we're forming hydrogen from water. I'm going to turn this microphone down a little bit. It's kind of reverberating. All right, let's see if that's better. So let's say we're taking water and we're decomposing it into hydrogen and oxygen, splitting it into hydrogen and oxygen. So the delta H for this reaction is 286 kilojoules, positive, so it's an endothermic reaction. And what this number specifically means is that if we take 1 mole of oxygen and we decompose it to make 1 mole of hydrogen and half a mole of oxygen, this is the enthalpy change, 286 kilojoules. So if we're going to produce 1 mole of hydrogen, that's going to be our enthalpy change. Delta H is going to be 286. But let's say we run the reaction on a larger scale and we produce 2 moles of hydrogen. Or alternatively, we double the coefficients for this reaction to make them all whole number coefficients. If we're producing twice as much hydrogen, we're going to have twice as much enthalpy change. The delta H will be 572, which is 2 times 286. All right, so when we change the coefficients in a chemical reaction, or experimentally when we run the reaction on a larger scale and are producing more product or consuming more reactant, that's going to cause our enthalpy change to scale by that same amount. So what this then means more specifically is if we have a reaction with a certain delta H associated with it, what happens when we reverse the order of a chemical reaction? So delta H is given by the enthalpy of the products minus the enthalpy of the reactants. And so if we change the order of the reaction, if the reactants become products and the products become reactants, if we flip the chemical equation over, then all that happens to delta H is that it changes its sign from positive to negative or negative to positive. So let's consider just another example of a reaction. Let's say we take magnesium carbonate, and if we heat this up, it will decompose to make magnesium oxide and carbon dioxide. This is an endothermic reaction. If we were to consider the reverse of this reaction, which is combining magnesium oxide with CO2 to make magnesium carbonate, so let's flip the reactants into products, MgO plus CO2 to form magnesium carbonate, MgCO3, the delta H for this reaction is just going to have the opposite sign. Same magnitude, 117, but it's going to be negative in this case. It's going to be an exothermic reaction, because if delta H is the enthalpy of the products minus enthalpy of reactants, if we flip reactants and products, the sign is going to change. That one should be fairly clear to us. And then, as we talked about on the last slide, if we adjust the coefficients for a chemical reaction, delta H scales by the same amount as the coefficients are scaled by. Okay, so if we take the reaction 2 magnesium carbonates and decompose it to 2 MgO plus 2 CO2, this is obviously not the lowest whole number set of coefficients, but it's taking this first reaction here and just doubling all the coefficients. The delta H for this is going to be double that of that first reaction. So it's going to be 2 times this value here, 117 kilojoules, or 234. And then if we were to take the coefficients and halve them, so let's say we just did 1/2 MgCO3 decomposing to 1/2 MgO plus 1/2 O2, sorry, CO2. Delta H for this is just going to be 1/2 times that original value of 117. Alright, so whenever we change the coefficients or change the order of a chemical reaction, we have to also then correspondingly change delta H. And we could do some combination too. We could flip a reaction and adjust its coefficients. So there's a lot of possibilities here. So this brings us then into a situation where we have what's called Hess's law, where we can add delta H for 2 different reactions or 2 or more different reactions. So we've seen how delta H changes when we change something about an individual reaction. Now let's see what happens when we combine 2 reactions together. So when we add reactions, the delta H's are also additive. So if we're adding together a bunch of chemical reactions, the total enthalpy change is going to be the enthalpy change for the first reaction that we're adding, plus the enthalpy change for the second reaction that we're adding, plus the third, and so on. However many reactions we're adding together in sequence, we're going to get a combined delta H that's just the sum of all of them. Alright? So if we take that reaction we just talked about, magnesium carbonate, and you make 2 MgO, so I don't want to do that yet, let's just coefficient of 1, sorry. MgO plus CO2 has a delta H of plus 117 as we saw. Now let's say we combine this chemical equation with another one, which is we take the CO2 from the first reaction and we combine it with H2 to make methanol and water, CH4O and water, just as a random example. The delta H for this reaction is minus 131 kilojoules. So if we add the 2 reactions together, we talked about adding chemical equations last time. We add up all the reactants, so MgCO3, H2, and CO2. We notice that CO2 is a product of the first reaction, it's a reactant in the second reaction, So it cancels out. It's what we call an intermediate. And so the overall reaction would be the hydrogenation of magnesium carbonate, MgCO3 plus 3H2 to make MgO plus CH4O plus water. The delta H for this reaction here, that's the combination of the two, is going to be the sum of the two delta H's. It's going to be the delta H for reaction 1 plus delta H for reaction 2. And then the second delta H is minus 131. So we get minus 14 kilojoules. Alright, so Hess's law of summation, or Hess's law as we just call it more simply, it allows us to combine two chemical reactions and calculate the delta H for the combined reaction based on the delta H's for the two reactions that we initially were combining. So the trick to this is we're not always going to give you the reactions in the correct form or the correct order. So here I gave you, MgCO3 going to MgO plus CO2, and then the second reaction had exactly 1 mole of CO2 on the reactant side. The intermediates canceled out, and we got the combined reaction. But what you're often going to have to be able to do is combine two chemical reactions to find a delta H, where one or more of those individual reactions, you're going to either have to flip the order of the reactants and products, or you're going to have to adjust the coefficients to make sure that the intermediates cancel out and that you end up with the overall reaction that you're interested in. So let's go and just do some examples of this. This is the best way to learn it. So let's say we want to figure out the enthalpy change for the dimerization of NO2. So we're going to take two NO2s and we're going to combine them together to make N2O4. So we're just going to stitch two together to make a molecule that's twice as big. We want to find delta H for this reaction, and we're given delta H for these two reactions here. One of them is N2 plus O2 to make NO2, and one of them is N2 plus O2 to make N2O4. So we have those two enthalpy changes. We want to try to figure out how do we combine these to find delta H for this reaction. So the first thing we have to figure out is how to add these two equations together in the right order, in the right sequence to get this overall reaction. So if we look at the first equation here, our first equation that we're given delta H for has NO2 as a product, one NO2 as a product, but then our overall reaction, which we're trying to find delta H, has two NO2s as a reactant. So if we want to get two NO2s on the reactant side, we have to take this first equation here, we have to flip the order, and we have to double the coefficient to put a 2 in front of there. So if we take minus 2 times equation 1, so let's remember these 1 and 2, that's equivalent to taking this first equation here, flipping it, and doubling the coefficients. We're going to do both things. So if we take the first equation, flip it, and double it, we get two NO2s going to N2 plus 2O2. So we've, again, doubled all the coefficients and flipped the order. And then the delta H for this modified equation is going to be minus 2 times the first delta H1 as I'll call it, which is minus 68 kilojoules. Alright, so we talked about the properties of delta H's. If we double the coefficients, we double the delta H. If we flip the order, we change the sign. So when we do both, it's equivalent to multiplying it by minus 2. So that gives us the delta H for this one. And then for the second equation, our overall reaction has N2O4 as a product. Our second equation has one N2O4 as a product already, so we shouldn't need to change anything about this equation. N2O4 is on the product side, and the coefficient is 1, just like we want it to be in our unknown, in the equation we're trying to find the unknown delta H for. So if we just take our second chemical equation and add it directly to that, N2 plus 2O2 goes to N2O4. Delta H for this is unmodified. It's just plus 10 kilojoules as it was given to us because we didn't change the coefficients or the order for the second equation. And now when we add these two together, we have N2 canceling out because it's a product in the first reaction and a reactant in the second. We have two O2s that cancel out that are formed in the first reaction, consumed in the second. And so our overall equation becomes the dimerization of 2NO2 to make N2O4. And the delta H for this is going to be the modified delta H for this equation, which is minus 2 times the first delta H, plus the second delta H. So all we're doing now is just adding these two numbers together, minus 68 plus 10, and that gives us minus 58. So these types of problems are in some ways kind of like doing a puzzle. You have to figure out how to piece together the given reactions to get the correct form of the chemical equation that you're interested in, and then use the properties of delta H and add those together appropriately to get the overall delta H for that reaction that we're trying to find delta H for. So the highest that will probably go, I don't want to say definitely, but I haven't looked at the problems that far in advance, but in general we're not going to go any higher than 3 equations. So this is a case that has 2 chemical equations. The more complex one, which is as complex as we'll see, is doing this for a reaction that has 3 chemical equations. So now we have to figure out how to add all 3 of these chemical equations together to get this chemical equation up here where we're trying to find delta H for that. All right, so the setup is the same. We have 3 known chemical equations with their associated delta H values, and we want to combine those in some way to get that reaction up there, that equation up there. All right, so once again we look at what we have going on here. So in this first equation we have C2H2 as a reactant, which should appear as a product in our overall reaction. And that's the only place C2H2 appears in any of these 3. So we know that we're going to have to take this first equation and we're going to have to flip it, because we want 1 C2H2 on the product side. Right now we have 1 C2H2 on the reactant. So if we take that first equation and flip it, it'll give us that product in the right orientation. So we can do this in a lot of different orders and in a lot of different ways, but I just like to work through them one at a time. So if we take the inverse of the first equation, we take this and we flip it. Again, let's number them to help us keep track, 1, 2, and 3. If we take the inverse of the first equation, we get 2CO2 plus H2O, and the products become C2H2 plus 5 halves O2. I'll leave out the states of matter because they're not really important for this exercise. And the delta H for this is going to be the negative of that first delta H. So we've taken this first equation and flipped it, so we have to flip the sign of delta H, which becomes 1299.5, positive number. For the second equation, we see that we have carbon as a reactant, and our overall equation has 2 carbons as a reactant. So we're going to double the second equation to make sure that when we add them all together, we have 2 carbons on the reaction side. So we're going to take this one and we're going to double it. So we get 2 carbons plus 2 O2s to form 2 CO2s. And the enthalpy change for this modified equation is going to be double that of delta H2. Alright, so we've doubled the second equation, so we're going to double its delta H accordingly. And we get minus 787 kilojoules, 393.5 times 2. And then finally for the last one, we see that our overall equation still has H2 as a reactant, and H2 appears as a reactant in this third equation here. It has a coefficient of 1. We want to have a coefficient of 1 in the overall reaction, so we're just going to keep this third equation exactly the same and not modify it. So we take our third equation unmodified. H2 plus 1/2 O2 goes to H2O. Delta H is unchanged and is minus 285.8. Alright, so then finally we want to add up the 3 equations, make sure that we added them correctly, that we modified them correctly, such that they add together to give our overall chemical equation with its unknown delta H. So if we look at what's going on here, we have 2 CO2s as a reactant, but they cancel out with the 2 CO2s that are a product in the second equation. H2O is a reactant in this first one here, but then it cancels out as a product in the last one. If we go back down to the rest of the reactants, we have 2 carbons that don't cancel out with anything, but our 2 O2s here, we have 2 O2s in this reaction, we have a half O2 in this reaction, so that's a total of 5 halves O2 on the reactant side, but those are going to cancel out with the 5 halves O2 that's on the product side of this first equation. So all the O2s cancel out, those are not going to appear in their overall equation. And then all that's left then is 2C from this equation on the reactant side, H2 from the third equation on the reactant side, and the only product that's not canceled out as an intermediate is C2H2, which comes from that first equation. Alright, so by adding the equations in that particular sequence, we get the overall chemical equation. And then the delta H for this is going to be just the sum of these three delta H values here that are modified from the original values. So it's going to be the 1299.5 plus minus 787 plus minus 285.8. And so if I did the math right, we get plus 226.7 kilojoules. Alright, so this was kind of a roundabout way to get there, but to find the delta H for the combination of carbon and hydrogen to make acetylene, all we had to do was just take these three reactions, modify them in different ways, add them together, and then we add the delta H's accordingly. Alright, so that's the idea with Hess's law. Alright, I'll do one more example of this just to show you how it works one more time. Again, with three equations. So in this case, let's try to find the enthalpy for this reaction, which is combining carbon with O2 to make CO2. Now, if we want to verify that this works, we saw that equation up here, I believe. Carbon plus O2 makes CO2. Delta H is minus 393.5. Let's see if it works out then that we can add together these three chemical equations, which have a whole other bunch of garbage in them, but if we add them up correctly to get this overall equation, do we get the same delta H that I gave you before? So this is a good way to verify that this method does indeed work. Alright, so this one's a little bit more roundabout way of doing it, but what we see is, again, in this overall equation here, we have CO2 as a product. We have one CO2 as a product. If we look at the given equations, for the first one here, we have one CO2 as a reactant. CO2 does not appear in any of the other equations, so we're going to flip this first equation, and that's going to put CO2 on the product side, which is where we want it for our overall chemical equation. So we take the inverse of equation 1, which means we flip the reactants and the products, and we flip the delta H, again numbering them to help us out. So delta H is going to be the negative of delta H1, which is plus 234 when we change the sign. Alright, if we look at the second equation here, this one doesn't have, well, this one has O2 in it, but we notice that O2 appears twice. So we don't want to try to balance O2 now because we want to have one O2 on the reactant side, but if we try to balance it with this equation here, by just flipping this, we also have to worry about the O2 that appears in the third equation. So sometimes it's helpful to go out of order here, so I'm going to skip equation 2 for now, but if you look at equation 3 has two carbons as a product. Our overall reaction has one carbon as a reactant. Carbon doesn't appear anywhere else, so if we take this third equation here and flip it, that's going to give us one carbon on the reactant side. Okay, so we're going to take, and we have to also then multiply it by a half. Sorry. Okay, so to reiterate what I just did, this has two carbons as a product. If we flip it, that puts two carbons on the reactant side. If we multiply it by 1/2, that changes the coefficient to 1, which is what we want for our overall chemical equation that we're dealing with here. So we take 1/2 times equation 3 and we flip it. So we get strontium plus carbon plus 3/2 O2 goes to make strontium carbonate. And the delta H for this modified equation is minus 1/2 times delta H3 because we've flipped and have the third reaction. So we do the same thing to delta H and we get a minus 1220 kilojoules. Alright, we still see that these don't quite add up to give us the overall reaction because we have strontium carbonate cancels out, so that works out. But we have strontium oxide that forms in this first reaction and is not canceled out in the second reaction. So we have to make sure that our intermediates that are left, SRO and SR, that they cancel out properly. So that's what we're going to use the second equation. So the second equation has SRO as a reactant, so that'll cancel out with this as a product, but we also have to multiply the coefficients by 1/2. So if we take 1/2 times equation 2, that's going to give us strontium oxide as a reactant, which will cancel out with this product in the first equation. It's going to give us strontium as a product, which will cancel out with the strontium as a reactant in this modified equation. So again, we can do this in sometimes different orders, but if we take 1/2 times equation 2, we get strontium oxide decomposing to strontium and 1/2 O2. Delta H is going to be 1/2 times the second delta H, because all we did to that was multiply the coefficients by 1/2, and so we get 592 kilojoules. We just take this delta H value here, divide it by 2. So when we add these together, we can now verify that we've done this correctly and that all of our intermediates cancel out and that we're left with the overall reaction. So strontium carbonate is a reactant in the first one, but it cancels out as a product in the second equation. Strontium is a reactant here, but it cancels out as a product down here. Okay, so we have carbon that's left, it doesn't cancel out with anything. Strontium oxide in the third equation, or the modified one up here, cancels out there. So all that's left on the reactant side is carbon, and then we have our O2s here. So for O2, we have 3/2 O2 as a reactant over here, and then we have 1/2 O2 as a product. So in net, we have 1 O2 on the reactant side, 3/2 O2, and then 1/2 as a product, and that is 1. So this one cancels out, and that cancels the coefficient to give us 1 O2. And then on the product side, everything else is canceled out except for CO2. Alright, so when we take this sort of convoluted sequence of reactions and add them together, all that's left is carbon plus O2 making CO2. Everything that has strontium in it cancels out, and then as I said here, we had 3/2 O2 partially canceling out with the 1/2 O2 to give in net 1 O2 as a reactant. Alright, so finally then we just have to add the delta H's. So we take the modified delta H's from these three equations and add them together, so it's going to be 234 minus 1220 let me rewrite that. And then plus 592 in the last one. And that comes out to minus 394, which is very close to that 393.5 value that I gave you in the last problem. Alright, so it doesn't seem like this should necessarily work, but if we add the equations together correctly, the delta H will add up correctly as well. Alright, so that's, that's kind of fun, depending on your definition of fun. You may enjoy that or you may not. But it's kind of, like I said, it's kind of like putting a puzzle together, and you'll have a lot of problems like this that you'll see in the upcoming homework assignments where you'll get to practice this, and certainly we'll have 1 or 2 on the next exam. However, that's obviously not the most practical way of doing things because, as I showed you here, we can take, pretty much any combination of random reactions, add them up, and get an unknown delta H. But there's really no, there's nothing systematic about that. Why would we pick these 3 reactions if we want to find the enthalpy for oxidizing carbon with oxygen to make CO2? That just seems, totally random, which it is. So there's a more systematic way to do this, which is what's called formation enthalpies, using what are called formation equations. So instead of just, typically speaking, instead of just using random chemical equations and adding them together using Hess's law to find unknown delta H's, we're going to use what's called enthalpy of formation to do that, which is a lot more direct way of going about it. So let's first define what a formation equation is. So a formation equation is a specific type of chemical equation and what exactly does it show? So as the name implies, it shows the formation of something, but what is that? So it's going to be 1 mole of a compound. Alright, so that's one key part, is that the product side is going to just have 1 mole of a compound. And what is it going to be? Where are we going to be forming that compound from? We're going to be forming the compound from elements in their standard states. Alright, so we'll have to talk a little bit more about what each of these means, especially the part about standard states. But basically a formation equation involves forming a compound from the elements that make it up. Alright, something to keep in mind with formation equations is that fractional coefficients are okay on the reactant side. Sometimes we'll need to have them, as we'll see. All right, so the product side, as I said, is 1 mole of a compound. So there's no coefficients on the product side, just a 1 or implied 1. But then the reactant side can have fractional coefficients if you need them. And the general form then is going to be, 2 or more elements combining to make 1 mole of a compound. So there's only going to be one product, and it's only going to have a coefficient of 1 in front of it, nothing else. So that's the general form for a formation equation. All right, so to understand this a little bit further, we need to start talking about elements in their standard states, because a formation equation will only have on the reactant side elements in their standard states. So what exactly does that refer to? So this is the first time we've seen this, I believe. So standard states refers to 2 different things. It refers to the state of matter, whether the element is a solid, a liquid, or a gas. And then it also refers to whether that element exists as a monoatomic species or something with more than one atom in the formula, and so on. So that's what we mean by standard state. What is, at normal conditions on Earth, how does that element exist in its natural state? So for the gases, there's going to be several elements that are gases, and these are all going to be nonmetals. So as the name implies, all noble gases exist as gases in their standard states. Although you're not going to see these in very many formation equations because there aren't very many compounds that involve noble gases. Now the other elements that are gases in their standard states are going to be many of the nonmetals. So hydrogen is a gas, as we probably already know, and it exists as H2. So hydrogen is one of our diatomic elements. The natural form of hydrogen is 2 hydrogen atoms bonded together, not just single hydrogen atoms, H2. N2 is a gas. It makes up most of our atmosphere. O2 we know is a gas because it's what we breathe. And then F2 and CO2. So these elements, the noble gases plus these 5, they all exist as gases. The noble gases are just single atoms, so neon, helium, and so on. But then these gases exist as diatomics: H2, N2, O2, F2, and Cl2. There are only 2 liquids in the entire periodic table, 2 elements that appear as liquids in their actual state. So one of those is the slightly heavier halogen bromine. That's a nasty red liquid, Br2. And then the only other liquid on the entire periodic table, which is fun, albeit somewhat dangerous to play with, is mercury, Hg. It's a metallic liquid, so kind of a weird one. But those are the only elements that exist as liquids in their standard states. And then again, bromine is a diatomic, Br2. Solids is everything else on the periodic table. So there's only 3 states of matter, so except for these few exceptions, everything else is a solid in its natural state. All right, there are roughly 118 elements on the periodic table, so with all but maybe 15 or so exceptions, they're all going to be existing as solids. Now there are a few examples of elements that are also polyatomic solids, which means they're not just single atoms in their smallest unit. They are polyatomic. So iodine exists as I2. So you notice that all of the halogens exist as diatomics. F2, Cl2 are gases, Br2 is a liquid, I2 is a solid, but they all are diatomic. And then there's a few other nonmetals that are polyatomic as well. Phosphorus' most stable standard state is P4. Sulfur is S8. And then the one right below sulfur, selenium, is also octanuclear, Se8. So those are the polyatomic solids as well. All the other solids, all the metals particularly, are going to be just monoatomic. So sodium is just Na, or iron is just Fe. But some of these, in the nonmetal cases, have polyatomic molecular forms. We'll talk more about these states a little bit later on in the course, but for now we just need to know what they are and know how to recognize what a standard state for an element is. And we'll talk later on about why they form these different states and more properties about them. All right, so those are the standard states of the elements, which is an important point for recognizing formation equations. And then, so finally, that brings us to the formal definition for standard enthalpy of formation, which, as the name implies, is the enthalpy change associated with a formation equation. Another word that you'll hear used to describe this often is heat of formation. It's kind of a colloquial way of saying it, but really it's an enthalpy change. So when you have a formation equation, whatever the delta H is for that reaction is called the enthalpy of formation for that compound. So we abbreviate it with delta H with a little F on it. Sometimes you'll see a little bit of a little circle here, a little, almost like a degree sign. That just means standard conditions, which you'll learn more about in Chem 2. But this is the abbreviation you'll often see, and it has a little F next to it to tell you that it's an enthalpy change specifically for a formation equation. All right? So there's about 118 delta H's of formation that you guys will have to know off the top of your head without us giving them to you. And those are going to be for the elements. So let's think about this for a second, thought problem. What is the standard enthalpy of formation for an element in its standard state? Is it going to be 0, positive, negative, or does that depend on the element? Heard a few people say it, I think. All right, you can say the letter or the word. All right, let's think about this for a second. So let's say we want to form H2 from the elements. Yeah, so I heard an A. I like that answer. So forming H2 from the elements would be forming H2 from H2. So when you're forming an element from an element, there's no net reaction, so there's no enthalpy change. Right? If the reactants and the products are the same, so the standard enthalpy of formation for any element on the periodic table in its standard state is 0. So if we give you an element as part of a chemical equation, we don't have to tell you what the enthalpy of formation is for that element. It's always going to be 0. All right, so hydrogen, helium, whatever element we have in the chemical equation, its delta H of formation will be 0. So now let's see one more little bit of a thought problem. I forgot to bring the clicker set up. We're not going to be able to do this interactively. We'll just have to shout out answers again. All right, so which of the following represents a formation equation? So we're talking about sodium carbonate here, which is a boring white powder, but which of these represents the formation for sodium carbonate? A, B, C, or D? Take a minute to think about it, and then you can start shouting out answers. Don't be shy. All right, so when we're thinking about formation equations, the two things we want to look for are, on the reaction side, we should only have elements in the standard state. They have to be in their standard states. And the other criterion is that the product side only has 1 mole of a compound for it to be a standard formation equation. So of these 4 choices, the only one that fits all of those criteria, let's look at it. So choice A has compounds as reactants. So that's not going to be a formation equation because the reactants are not elements, but they are compounds. If we look at choice B looks pretty good. We have sodium is the standard state, Na is the standard state for sodium, carbon, C is the standard state for carbon, and then we have O2 is the standard state for oxygen. That's one of our diatomics. And the product side only has 1 mole of a compound, so that's going to be our correct answer. If we look at the rest of these, we see that in choice C, it's a balanced chemical equation. It's forming a compound from the elements, but we notice that we have a coefficient of 2 on the product side. And a formation equation only specifically refers to forming 1 mole of a compound. So basically, choice C is 2 times the formation of sodium carbonate. And then finally, for choice D, it looks like it might be okay. It's going to have, 1 mole of a product, 1 mole of a compound. Looks like it's all elements, but remember that the standard state for oxygen is O2. So oxygen by itself, O, is not the standard state for O2, so it has to be in a standard state to be in a formation equation. All right, so that's part of what we'll ask you to do conceptually, is just being able to recognize what is the proper form for a formation equation. All right, but what's the more important part that we're going to get into last today is how do we use delta H of formation to find any delta H for a chemical reaction. So we have a very simple equation. It's similar to the one that we've seen before, which is that The enthalpy for a chemical reaction, delta H, the enthalpy change, is going to be the sum of the delta H's of formation for the products minus the sum of delta H of formation for the reactants. Alright, so if we know the formation enthalpies, if we know delta H of formation for all of the products in the reaction and all of the reactants, we can calculate delta H for any chemical reaction. And this is sort of the way that we typically do it, is that we tabulate delta H of formation for all kinds of compounds out there, and then when we want to do a chemical reaction with those compounds, we can calculate the delta H for that chemical reaction using the formation enthalpies. So just to remind ourselves what some of these terms mean, this Greek letter here is a sigma, which means you sum them up. And then these M and N that I have here in generic form, these are the coefficients for each reactant and product. Okay, because the formation enthalpy refers to the formation of 1 mole of that compound. So if we want to use it in calculating enthalpy of formation, or sorry, enthalpy of reaction, if there's something other than 1 mole of that compound, we have to adjust its formation enthalpy accordingly by multiplying it by the correct coefficient for the balanced reaction. So this is very similar to the equation that we used before to calculate delta E using bond energies. But remember, in that case, it was reactants minus products. We have to keep the two straight. Here, because delta H of formation is defined as forming a product, forming a compound, we're going to take the delta H of formation for the products and subtract the delta H of formation for the reactants. It's sort of the opposite of what we saw for bond energies, but it's really the same type of equation. You sum up all of the delta H's of formation on one side, you sum up all the delta H's of formation on the other side, and you subtract them to products minus reactants. And remember, don't forget for this, that any element that appears in your chemical equation have a delta H of formation equal to 0, so any element that's in there we can ignore when we're calculating delta H using delta H of formation. Alright, so let's see 2 examples just to close out how we use delta H of formation to calculate the delta H for a reaction. Alright, so let's do the combustion of methane first. So we have CH4 burning in the presence of O2 to make CO2 and water. We should recognize that this is a combustion reaction because we're burning a hydrocarbon and making carbon dioxide and water. My pointer died at the worst time. We're almost done. I have to change the batteries. Okay, so just give me a second. Okay, so we want to find the delta H for this reaction where we're giving you the delta H of formation for methane, this is minus 74.9. The delta H of formation for CO2 is minus 393.5. And the delta H of formation for water is minus 241.8. So I gave you all 3 of those delta H of formation. So the delta H for the reaction, remember, it's going to be the sum of all the delta H's for the products, the formation delta H's, minus the sum for the reactants. Okay, so that's the general equation. So if we do this for the product side, on our product side we have 1 mole of CO2. So we're going to use the coefficient of 1, and we're going to multiply that by the delta H of formation for CO2, which is minus 393.5. So you notice that all of the formation enthalpies are given to us in kilojoules per mole, because it's formation of 1 mole of that compound. Okay, so we have 1 mole of CO2, and we multiply that by the minus 393.5. Our other product is water, so it's going to be 2 moles of water formed as a product. We have a 2 in front of our H2O. And the enthalpy of formation for water is given to us as minus 241.8. Alright, so that's the sum of the delta H's of formation for the products. 1 CO2 plus 2 waters. And then we're going to subtract the sum of the delta H's of formation for the reactants. So on the reactant side we have 1 mole of CH4, and its delta H of formation is going to be given to us as minus 74.9. And then we have to add, we have 2 O2s. And what's the delta H of formation for O2? 0. Remember, O2 is an element in its standard state. So the delta H of formation for O2, which we didn't give you, is 0. And if we don't give it to you, that probably means it's 0, because that's the only one you'd ever have to know off the top of your head. Alright, so we can just ignore that one. That doesn't really matter. And so finally what we get when we add the two reactants, add the two products, subtract the reactant, is going to be minus 802.2 kilojoules. Alright, so when we burn 1 mole of CH4, we get a delta H of minus 802.2 kilojoules, and we calculate that by using the formation enthalpies for the products and the reactants. Alright, one final example of any questions on that before I move on? Alright, one final example, same exact approach, just a slightly more complex reaction. Let's take another form of phosphorus, it's called red phosphorus. Let's take red phosphorus, combine it with nitric acid, and then make phosphoric acid. So this is a way to make phosphoric acid where we release NO2 as a byproduct and also water. We want to know the delta H for this reaction. Alright, so on the product side we have water, phosphoric acid, and NO2, so it's going to be, this reaction is balanced, we have 1 water, so it's going to be 1 times the delta H of formation for water. Another slight subtlety here that I should have pointed out is that we notice here we have liquid water, and the formation enthalpy for liquid water is a little bit different than the formation enthalpy for gaseous water. So the formation enthalpy also depends on whether it's a solid, liquid, or a gas. So the states of matter can be important sometimes. So we have, anyway, getting back to this, on our product side we have 1 water, we have phosphoric acid, so we're going to take the delta H of formation for phosphoric acid and multiply it by 1. And then our other product is going to be NO2, and we have 5 of those, so it's going to be 5 times the delta H of formation for NO2. So that's the sum of the product side, and then we're going to subtract everything on the reaction side. So here's again where we have to be a little bit careful and not breeze through things too quickly. So here we're using a form of phosphorus called red phosphorus, which is monoatomic. And we notice that this is not the standard state for phosphorus. The standard state for phosphorus is P4. So we don't want to assume this is 0. If we look at the given information, we see that red phosphorus has a small enthalpy of formation because it's not the standard state for elemental phosphorus. There's some enthalpy change when you convert the standard state, which is P4, into red phosphorus. So we're going to have to use the delta H of formation for red phosphorus, which is given to us. And then the other reactant is going to be HNO3, so we have to use 5 times the delta H of formation of HNO3. Alright, so now we just have to put the numbers in and do the math. So we get the delta H formation for liquid water is minus 285.84. We add to that the 1 times the delta H of formation of phosphoric acid, which is given to us as minus 1271.7. And then the last product is NO2. We have 5 moles of NO2. Delta H of formation for NO2 is plus 33.2. Alright, so the most common mistakes in these problems are sign errors. You have to make sure you have the right sign for everything. And then we're going to subtract the delta H's of formation added together on the reactant side. So we have 1 mole of red phosphorus. And the delta H formation for red phosphorus is minus 17.6 kilojoules per mole. Then we have 5 moles of nitric acid as a reactant. And the delta H formation for nitric acid is 173.33. And so when we do all the addition and subtraction for this, we should get something like minus 507.29 kilojoules. Alright, so same exact situation. We're using delta H of formation to calculate the delta H for reaction. All right, so that'll be something we'll see a bit more of in the future. But best wishes on your exam this week, and if you still haven't taken it yet, please come find me if you have any questions.